So in this video, we're going to talk about the most fundamental ways that you can actually connect components in a circuit, and that is the idea of connecting things in either series or in parallel. In addition, we're going to look at an application of why you might wish to connect items in series. So when you have actual components within a circuit, there's two fundamental ways that you can connect them if they each have two nodes or points of connection. And the easiest way to see this is kind of just extend your hand out like this. Extend your thumb and your pinky out on both sides. If you were to take the component that corresponds to your left hand and the component that corresponds to your right hand, and you were to pick one actual node of each, so say your thumb, and you were to connect those two nodes together, that is referred to as a series connection. If instead you were to take and connect both common nodes together, that would be referred to as a parallel connection. And you can actually see how those connections look when they're represented in a schematic on the bottom. Namely, here, the bottom ideal DC voltage source and the top ideal DC voltage source. If you notice that both of those, next to them, the schematic has a rated value of 5 volts. In addition, it has a reference designator to kind of say which voltage source is which. The bottom is denoted as V1 and the top is denoted as V2. They share one common point of connection. The negative terminal of V2 is connected to the positive terminal of V1. So we say that these two things are in series. And really the technical definition of what makes two components in series is if two components have the same current through them, then they are said to be in series. In contrast, here on the right, components V3 and V4, the ideal voltage source, if you notice, they share a common connection at their positive terminals, along with a common connection at their negative terminals. We say that these two are in parallel. And when they're drawn, they kind of look like they're parallel next to one another. So that kind of makes sense. And when components are in parallel, they have to have the same voltage across them. So for now, the only components we've talked about are DC voltage sources. However, we're going to actually talk about the idea of resistors a little bit later in part 2 of this lecture. And you'll see that this idea of connecting in series or parallel and the fact that when they're in series, it's the same current. And when they're in parallel, it's the same voltage, extends beyond just this idea of voltage sources. So one thing you might note that if it's kind of confuses some people on the right, if there were no additional components connected to this, in addition to being in parallel, these would also be in series. So when we actually analyze simple DC circuits, we're going to see that when you just have a single source and a single load, they're both in parallel and in series. So just keep that in the back of your mind for now, but everything else holds. So why would you actually ever connect components in series, particular DC voltage sources? So if I combine multiple DC voltage sources in series, what that's going to allow me to do is to generate new voltage levels that aren't equivalent to either of the individual single voltage levels. So what we have on the right here, this is a basic idea of what's known as a series aiding connection. And the reason it's called a series aiding connection is I have the positive terminal of one voltage source on the bottom here, V2, connected to the negative terminal of the upper voltage source, V1. And what that means is if I move across both voltage sources, in each case, when I go from the bottom to the middle and the middle to the top, I'm going across a rise. So I'm kind of stepping up in both scenarios. So the polarity of these sources is combined in series in such a way that as someone moves across, they step up combined in voltage. So this is known as actually a series aiding voltage source connection. And what it allows you to do is to create effectively a single voltage source, a V1 plus V2, across the outer terminals of both of these. And the next learning module, which we won't actually cover to part 2 of the DC voltage lecture, which will be next week, is going to introduce us to the idea of how to do nodal voltage analysis and actually deal with when we have multiple voltage sources or maybe when they don't even share the same polarity. But let's just look at a quick example of seeing if we can actually identify whether some components are in series or in parallel and so on and so forth. So say we have this complicated circuit below. It has an ideal voltage source. We've talked about that before. It has an ideal current source. Just don't worry about what the symbol down here means for now. We'll see that in the next module when we get to it. It's the reference designator. It's the point from which we're going to measure all nodal voltages. Oftentimes it's called a ground. But in addition to the DC voltage source and the DC current source, we also have a bunch of resistors, a 20 ohm resistor, a 6 ohm, and a 5 ohm resistor. So what we're asked is to determine whether or not the 6 ohm and 5 ohm resistor are connected in parallel or series. So let's focus in on them. Here's the 6 ohm resistor. That's how you pronounce that Greek letter omega. We'll have an entire module on resistors in the next lecture on DC circuits. Here's the 5 ohm resistor. So if you notice, both have 2 points of connection. They're both 2 node components. And this node of the 6 ohm resistor is connected directly. There's just that horizontal line drawn, and what that means is a perfect electrical connection with this node of the resistor, the 5 ohm resistor. So they share one common point of connection here, and they share another common point of connection here. So it's kind of like if you viewed the resistors as your hands and you made this connection, they are connected in parallel. So that is true. They are connected in parallel, not in series. Are any other components connected in parallel? Well, if you look, this 18 amp ideal current source, it's also in parallel with both the 5 ohm resistor and the 6 ohm resistor. So all three of these things are in parallel. Versus what's in series? Well, in series, we have the 140 volt source connected in series to the 20 ohm resistor. So these two things are in series, and these three things are in parallel. Another example here, consider the interconnection of voltage sources shown on the right. What is the effective voltage across the connection? Which node, A or B, is at higher potential? And what would happen if you measured the voltage with the opposite polarity? So if we notice what's going on here, the schematic symbols, these are just ideal voltage sources. All of them have a negative terminal at the bottom and a positive terminal at the top. So in moving from this node to this node, I go across a rise of 1 volt. In moving from this node to this node, I go across a rise of 2 volts. And in moving from this node to node A, I go across a rise of another 5 volts. So from the bottom, it's up 1, up 2, up 5. So in total, I went up 1, 3, 8. So node A, because of these three voltage sources, is 8 volts higher than node B. So that is the effective voltage across these three ideal voltage sources, which are connected in series in a series 8 configuration. Which node is at higher potential? Well, node A is at higher potential than node B, particularly it's 8 volts higher than node B. And what would happen if we reverse the polarity of the voltage that we were measuring? If instead of measuring with respect to A to B, we measured with respect to B to A, well, notice that B is actually going to be 8 volts lower than A. So if we were to talk about VBA, I would say that it's actually minus 8 volts. And the reason I'm doing this example is just to foreshadow a bit to what we're going to hit in the first module of our second lecture on DC circuits, which we'll do next week. But hopefully that did make sense to you. So just to kind of round out what we're going to talk about or do for this week, you are going to have a homework assignment that covers the 4 modules that I did originally. It should be pretty straightforward and pretty simple. And we're also going to do a lab where we're going to get some experience actually laying these basic components out in multi-cell.